Okay, guys, so this is our 10th ML Monday of this semester. Today we're going to be doing autoencoders and GANs, general serial adversarial networks. Um, so, bit of an introduction. This is my second ML lecture. I'm Kartik. I'm one of the ML lecturers. Again, if you have any questions, any comments, anything, you can reach out to me on LinkedIn or my email or any of the other ML lecturers. Okay, so a bit of a review about our previous lectures before we kind of dive into autoencoders and GANs. So, what is a deep neural network? As you should know by now, a deep neural network is a network with two or more hidden layers. A traditional neural network doesn't have that specific constraint. Most neural network architectures in modern day applications are actually deep. I've really personally heard anyone say they're using a traditional neural network. And some common ones on the screen right there are ResNet 18 and GPT-2. I think ResNet 18 has several million parameters, and GPT-2 specifically has I think it's somewhere around 200 to 300 million. I don't know. I might be wrong with that number. But long story short, a lot of these architectures have more than just two layers. I think the latest GPT ones, they don't disclose the amount of layers, but as you can assume, it's going to be way more than just 48. And I did this visualization in my last lecture, which was not too long ago. I think it was 3 weeks ago. Kind of like a little bit of like how neural networks work um, from like a visual standpoint. I mean, if we choose like a ReLU activation function, you can kind of see how a neural network understands the decision boundary of the points. So as you see here, the kind of like the background is what the neural network is using to base its decisions. And obviously the orange points are in the orange background and the blue points are in the blue background. That means the neural network is making accurate predictions. We can see different distributions. Right here, we see that all the orange points, again, the neural network learns the decision boundary correctly, and all the blue points are in the correct region, the orange points are in the correct region, and we kind of add layers to see how that affects the speed at which the model learns, the quality of the inference, just a little bit of visualization. And then next, let's kind of get into our main topic for today, autoencoders. So an autoencoder is a little bit different from a traditional neural network in the sense that we're not necessarily trying to predict or kind of classify something that we might traditionally try to do. So it's basically a network that is simply trained to produce an input as an output, but there's a latent space restriction. That's the main thing. And so what I mean by a latent space restriction is that the network has kind of like a bottleneck um, where there's only like a couple of neurons or a relatively low amount of neurons compared to the other layers, right? So if we look at this little graphic over here, we have 6 neurons at the start and 6 neurons at the end, and we kind of see like a bottleneck effect where the number of neurons start to decrease towards the middle, and that's our latent space. We're forcing the neurons to capture as much information as possible in the smallest amount of data possible, right? And then we use that information, those vector spaces again, to reproduce that into an output, and kind of we have what is called a reconstructed data, what is basically our input. And I mean, right off the get-go, you might be like, hey, why do I need to do this if we're going to end up with the original image, probably worse? So there's various types of autoencoders, which we'll get into on the next slide. But one of a couple of reasons why you might want to do this is the latent space can be key in certain use cases, mainly because it's usually a lower dimension, and it's lower dimension than our initial input. And in certain cases, you might have what's called a denoising autoencoder. You might have variational autoencoders. These are autoencoders with a specified purpose. So denoising autoencoder is we might input an image with maybe a little bit of noise, some extra pixel manipulation, and we might pass it through the autoencoder system. And we're basically trying to compare the output image against the image without the noise. So we're trying to update the network so that it can remove the noise. Um, and basically what we have there is basically a network that can kind of manipulate images to kind of have a little bit of generation as well, so they look like an actual image without the noise. and that can be useful in various cases. Yeah, so a latent space is a lower dimensional space in which we can capture data. Basically, again, simple fact is that there's less neurons in the middle layer compared to the outer layer, so the neurons are being forced to kind of compress the information. Compress is a good way of putting that. All right, so here are the autoencoder types. We have deep, which is multiple hidden layers. So this could be fully connected, convolutional, etc. With that, there's not really much of a restriction there. Sparse, you have a large bottleneck layer, meaning that there's more kind of like separation between the neurons. They're connected to all the different types of neurons before, but there's actually less neurons since there's going to be sparse. So that means the layer is going to be it's going to be spread out, but there's going to be less neurons overall. And what we're doing that is we're forcing the compression to be even more powerful. And so we're trying to capture even more information in a single neuron, right? And in certain situations that may work, certain situations that may backfire, but that nevertheless is a type of neural network. And then we have denoising neural networks, which is again what I discussed earlier, where we add noise to the input so the network can learn more robust features and how to remove the noise. And when we're actually updating the network, we're comparing the output against the image without the noise, not the image with the noise, because again, then we're just going to learn to reproduce the image with noise, which is not what we want to do. We want to remove the noise, right? So there's a bit of a discrepancy there that's important to note. And then we have the most complicated type of autoencoders, which are variational autoencoders. These are generative models. And how that works is it's a bit complex, so I'm not going to go into a lot of detail, but the input is actually not a fixed encoded vector or a point, which basically means that we're not actually passing in a specific point or a data. We're instead passing in a distribution of data points made up of the mean, the standard deviation, right? And so the model is actually forced to learn kind of the distribution of the data, the different possibilities, rather than the actual point itself, right? We're adding variation, said by the name. And so nearby points are going to produce similar inputs, right? And so nearby, there's going to be a sense where, okay, since we're not learning the exact point and we're learning a distribution, there's a generative capability, and that something might be slightly altered in the distribution, but we're still generating something that may look like a real image. Does anyone have any questions so far before we kind of get into a demo? Yeah.
Can autoencoders be used to like summarize like text? Like if you get an input and then like translate it, like when it encodes, it makes it just like some of its parts and then it
Yeah.
encodes it.
Yeah, definitely you can. I mean, the way that would work again is your input would be your large text, right? And then you pass it through the autoencoder, and then your output would be the summary. But again, you're going to have to update it against a certain summary. To train the model, you're going to need the summary of that specific text. So yeah, you can definitely do that as long as you know what your desired output is for each individual input. So in this case, autoencoders are a supervised learning method where for each input case, you must have the exact output. And in your case, the summaries for each training set where you have maybe like, I don't know, like a book or a paragraph, you need to have its summary for the model to train, right? We don't want you to just, in this case, we're not exactly trying to reproduce the output, but yeah. Yeah, so the capabilities of autoencoders extend more than just images. They're text models as well. I think there's something called encoder decoder networks, which aren't really the exact thing. I think they're a little bit different, but there's a lot of text models that work like that. I think GPT, well, I know GPT is a decoder only network, so there's no encoding space in that. So the whole layer where the bottleneck, that whole layer is removed, you just have a decoder, and that's a bit complex. But yeah, so autoencoders can be applied to more than just images. They've been used a lot for text. I think one of the most prominent ones off the top of my head I can think of is Flan from Google. I think it's a pretty big one. They have various versions. I think Meta has one too. You can just kind of hop on right here. Yeah. So this one is a transformer. This one has transformers, but it's a language model that has encoders and decoders. Okay, I can't find much details on it. Let's just say it's text to text, right? So what this usually means when you have text to text is you're putting a text as input and you're putting a text as output, and there's an encoding and decoding part of the network, kind of where we have in autoencoders. Yeah. So, any other questions? No. Okay. So we're gonna go into a little bit of a demo. I've linked it in the slides, but we're gonna use MNIST to kind of demonstrate an autoencoder right here. Can you guys see the screen, or is it too light? Okay. So the original demo was from a Geeks for Geeks page, which I kind of adapted myself and changed a little bit of things. That's where I mainly drew the inspiration from. And so we're going to be using the same MNIST data set, which is digits, scaled very low. I think it's 28 by 28. We're going to start off by importing all our packages. Are you guys familiar with PyTorch from the previous lectures? Yes? Okay. So we're going to be using PyTorch. Actually, I don't know if I'm using a GPU for this. We need a GPU. Okay. Yeah, we're using a GPU. Hopefully I don't run out in the middle of the lecture. It'd be embarrassing. Yeah, so for this little demo, we're going to use Torch and we're going to use matplotlib. So nothing crazy, not a lot of data pre-processing going on. We're going to focus on the neural network architecture, actually writing that code. Well, it's already written, so just kind of demonstrating that. I'm going to comment this out. I think I should be able to do that, right? No, it's not how Python works. Shoot. Okay, so I'm going to comment these 3 lines out first. So the first thing we do is we set up a transformation to transfer all our images to a tensor. What that basically is we're squashing the values of the pixels to be between 0 and 1 and kind of enabling it to use the GPU and actually train the model. And then we set up our data set where we download the data, we set the train to true, and we set up our transform pipeline. Basically, when we download the data, we'll be converting it to tensors, and then we use a data loader. Does anyone remember what a data loader is from past lectures? So a data loader is basically during training, we can access all of our data in batches for each iteration. And so the data loader kind of optimizes that. It's basically another way of just kind of accessing or storing the data, like kind of it's like packaging it in little boxes. And then every like training iteration, we're opening each box, training the model, throwing it away. And then at the end, we do all the process again with the same data, the whole process again with the data. So that's what a data loader is. It's nothing crazy. And then we have our actual architecture here, where we have the autoencoder. First, we define it using object-oriented programming. So this layer is our encoder layer right here, where we have first our linear layer, 28 by 28, taking the input. It's flattened, it's a fully connected layer. Then we flatten it to 128. Then we have a 64 neuron layer, a 32, and you can see we eventually get to an 8 neuron layer. And all these layers have ReLU separating them. Does anyone know what are some of the other options besides ReLU? ReLU, I don't know how to pronounce it. Just did that just happen? Okay. Anyone remember from specifically regularization? No? Yes?
Sigmoid?
That's an activation function. Wait, no, it is both of them are activation functions, but you can't use sigmoid there. Like there's specific variations of ReLU that you can use. What was that?
Leaky ReLU?
Yeah, there's leaky ReLU. There's a couple other ones. So leaky ReLU has more regularization with that. We can pop into the documentations right here. All these are activation functions. Sigmoid is also an activation function as well. But you don't want to use sigmoid there because the way it works is sigmoid's not going to help you kind of squash the values to either 0 or whatever it's best if I just show a graph, honestly, right here. right here. So there's going to be with ReLU, you can have kind of like, you can avoid the problem of vanishing gradients, right? Where the gradient's never really going to be like really, really low. With sigmoid, that kind of happens. It's a bit of intricacy with that. But with usually between the layers, we use ReLU. And leaky ReLU allows for a negative slope, so it allows for negative values, right? So that basically the problem with that is sometimes when you use traditional ReLU, the model will stop updating since it's basically zero. With ReLU, we still allow for a little bit of updates. So that's a little bit of variation with that. We could use decoders, the same thing, but in reverse. We do 8 to 16, 16 to 32. And then we have our forward function, which is basically, again, we take the input, we first put it through our encoder, then we put it through our decoder, and then we're missing something here. Does anyone have any ideas? What could go here? It's an activation function.
It's not a classification problem.
Yeah.
So it's
Mhm.
not software.
That's a good, yep. No, it's not softmax. So a couple of options we have. We have TANH. You can just pull up a picture probably. Activation functions. These are some activation functions. This is a good little graphic we have right here. This one doesn't have softmax, but as you can see here, ReLU, you kind of see that we avoid the problem by having either, we have kind of like a polarization with our outputs. There's other ones, there's ELU, there's ReLU with negative values allowed. TANH, sigmoid. Anyone have any guesses? So for this one, because when we use the transforms tensor for each pixel, that squashes it between 0 and 1. We're going to be using the sigmoid function because this transforms all the data back into 0 and 1s. So we want to be able to do that. So right here, we're just going to implement nn.sigmoid. Not write two n's there. Yeah. So basically, now we kind of have our full model via PyTorch. Not too complicated. And then if you can see, we're going to use mean squared error loss. Specifically, again, because we want to update, yeah. Oh, that's right. For loss function, we're going to use mean squared error loss. Basically, that's the way we're going to check our reconstruction of the image against the original image and try to update it using that. Does anyone remember what other model we use mean squared error loss for specifically? I was at the start. We used it a lot for linear regression. That was one of our main methods to optimize that. And for neural networks, we used, I think it was a mixture of binary cross entropy loss and cross entropy loss. Binary for binary classification and cross entropy loss for multi-class or multi-label classification. Mainly because those functions, again, are convex. So when we use gradients, we can update them towards an extrema where we're guaranteed to kind of have an optimal value, or our weights are going to have converse an optimal value. And then we set our learning rate. For the sake of the demo, I haven't set it to anything. Does anyone have any ideas? We could start off by. Yeah. 0.01. We're going to start off with that. And this is basically, we're setting up our device. CUDA is the GPU that we're going to be using for training. This is our training loop. So nothing too crazy here. We're going to train it for 20 epochs, which is 20 iterations of the data set. We're going to first we're going to compress it into the format that our neural network takes it in, right, from whatever format it was originally. And then we're going to reconstruct the images using them. We're going to pass it through the model. We're going to use that to kind of generate our loss. And then we're going to step our optimizer, basically update the function. With that, we're going to append the losses to our loss list, which is basically going to show, like, over time we can kind of see that. This is from the previous run that I did last night while writing some of this. This is going to take a bit of time, right? And I kind of wanted to show that it's going to take forever for the first epoch to even load. Yeah, so it's going to take, it took like around like 10 to 15 seconds. So one of the main things that we can do to kind of optimize these types of things is obviously we can lower the amount of epochs. But in this case, MNIST has 70,000 images, right? And so for this specific purpose, or if we're building a model, we might not want to use the entire data set. And so in this case, there's a library called Subset. Well, it's not a library. It's a module from Torch called Subset, where we can set up certain indexes that we can randomize to use. So in this case, we are going to use, let's say, 7,500 data points. That's basically 10% of the actual data set. And if we actually kind of run through the model, it shouldn't be too bad because, again, our autoencoder is relatively simple. See, it's updating pretty fast. And we're getting a pretty good sense of convergence. There's a little bit of a spike, which means our learning rate's a bit too high. Might want to update that to be a little lower if possible. So we updated our learning rate. We took only 7,500 samples. And now we should have a pretty good sense of convergence. Yeah. So we're seeing the loss go down, basically meaning that the autoencoder is learning to reproduce the input as output. Obviously, there's mistakes, hence the loss, but it's doing a fairly well job each time, which means our model is learning. This one's trained for 20 epochs, where we hit 0.03, which is pretty good. It's still spiking a little, so I think it's still a little too high. But if we look at the loss curve, it's converging pretty nicely. And if we look at some of this code, which don't have to really go over because it's not relevant to the particular model, but it's basically, we can look at some of the reconstructions that the autoencoder did. So we have 7, 5, 2, 0, 3. You can see the reconstructions are fairly accurate sometimes. Most of the times, actually, this turned into an 8. And this is not like a mistake because obviously, well, it is a mistake, but it's not that the model made like an unintentional mistake. Obviously, the model interpreted that in a way where it was used to storing those types of numbers as 8s. So when it was reproducing them, it kind of messed up there. That would be fixed with something like obviously more data, more training. But for the most part, you can see that the reconstructions have been pretty useful, right? And if we look at this, which is pretty interesting, our original pixel values are 28 by 28. I think it's like out of 256. This is the latent space vectors for each of the images. This is considerably lower than our original representation. So if we were to use this autoencoder to kind of preserve, I guess, the dimensions of the image, which can be very important in other types of models, other types of applications, would be pretty successful in the sense that we basically reduce it down to like 8 or 9 like values in the vector space. So that was something pretty cool that I wanted to show you guys. But these are 31 images. They're basically extracted from just running the encoder on the image. So this is used in like a lot of other applications as well. When we have like different types of models, sometimes we might do multi-model training where we have maybe images and we encode them in a shared vector space between texts, so we can look them up like a text input, right? So if we have like 10 images of cats and we want to look up an image with a cat with black spots or something like that, that's kind of how that would work. There'd be a shared embedding space, and the vector embeddings like this would be basically compatible for both text and image lookups. So that's the tutorial for autoencoders. Moving on to generative adversarial networks. This one's a bit complicated, definitely harder to train. I trained a couple at my internship last summer, and is by no means fun at all. I had to scratch that entire idea. But GANs are basically a network that is made up of two components, generator and the discriminator. And the generator basically takes random noise, just maybe a bunch of pixel values, and it turns that into what is kind of known as the fake image, right? And the discriminator, right, is responsible to take that fake image and a real image from a data set that basically those two images are kind of supposed to be similar, and the discriminator tells, oh, this one's fake, this one's real, right? And then so the generator takes feedback from the discriminator and it tries to get better at making fake images and try to fool the discriminator. And it's kind of like a back and forth process where the generator is coming up with fake images, the discriminator is trying to distinguish them, the generator takes that loss and that output from the generator, the discriminator, and updates its model. So both models are getting better at the same time, and they're getting better at what they respectively do. So the discriminator at identifying fake and real images, and the generator gets better at generating actual images. And the crux of this lies where we want to use the generator to actually generate images. That's the actual use case of this model. Is now we can use the generator. It's gotten so good that it can fool the discriminator, or it's just in general, its loss is very low to the point where it can be applicable. Um, so here's a little graphic that explains it a little bit more nicely than I do. We have fake images, noise, we generate into a fake generated example, and then we pull some real examples from our data set. Then we have our discriminator judges which ones are real and fake, and we do it all over again. The generator relying on the discriminator's output, and the discriminator relying on the generator's output. So there's a bit of an interdependency with that. The biggest thing about this when training is usually if not done properly, which is really hard to do, the generator will kind of fall back from the discriminator. You'll notice that the discriminator will start to have a really, really low loss and the generator will fall behind, which basically means that the generator has kind of lost its value in generating the fake generated examples because the discriminator is able to pick them apart really easily. And that's usually what happens. So trying to perfect that and nitpick it to the point where both of them are trained really well is hard because obviously there's a lot of synchronization and testing involved. Um, so here's a little bit of an informal training process. The discriminator, you take p points from a data set of real images, you run the generator to produce another p points. These ones are fake, obviously, and then you train the discriminator on these two sets of p points, right, to distinguish between which ones are real and which ones are fake. So the discriminator is a classifier, basically, at its core. The generator, you freeze the weights of the discriminator because, again, we only want to update the weights of the generator. And then we run the generator to produce p fake points, and we give it to the discriminator, and that's where the overlap occurs between both processes. And then we use the outputs from the discriminator to propagate and train the generator. A lot of training and discriminating and generating involved. Anyone have any questions so far? Yeah.
How the generator uses the outputs from the discriminator to keep it from.
The exact process I don't remember off the top of my head. I think it's. You could just look it up. Let's see. It's how the generator. It's a good question. Just don't remember that off the top. Yeah, so it's obviously through a loss function, but the exact outputs. Yeah, I don't know the exact outputs which the generator uses because obviously it doesn't use. The fake sample is passed to the discriminator, which classifies it as real or fake. Okay. So the loss basically, obviously all these models are updated using a loss, but this loss specifically is quantifying how well the generator is fooling the discriminator. So there's a bit of calculation involved with that. So if the generator, let's say, produces an image and the discriminator classifies it as a 1 versus 1 to 0, then against that little distribution right there, the generator knows that, okay, I did a good job here, right? So it can either, using the vector gradients, it can update that model in that direction. Whereas if it's not doing so well in this particular distribution, then it goes the other way. So yeah, that was a good question. Yeah, and then the discriminator is obviously going to be trained on the same sense that we have classification models trained on between 0 and 1. If it misclassifies, then it goes based off of traditional gradients. Okay, so here's a little bit of a demo. This one, I didn't really turn it into a notebook. Just going to kind of go through the code, mainly because this model doesn't really work. I've tried it. It has the same issue that I mentioned earlier. But they start off by kind of, let me make this bigger. They start off by importing the libraries, very similar libraries that we used. Was it freezing? We used last time. The generator is a bit complex since there's a little bit of convolutional layers. We transpose the layers into convolutional layers, and we have a bit of unflattening. So we initially take it as a fully connected layer. We flatten the image into basically a one-dimensional vector, and then we unflattened it into two-dimensional space, and then we do a little bit of convolutional work on that. And then we have tan h is used as our activation function, which I'm pretty sure the pixel values is -1 and 1, which doesn't make sense, honestly. Why? So there's no specific answer. Saying steeper gradients, but that's very generic. Why are they using -1? I don't know. Maybe it's easier for the. Maybe that's what I think the discriminator's input is. Yeah, because again, all this output is being passed into the discriminator. I don't know. I don't have a specific answer for that. But here's our discriminator function. Here we're trying to basically flatten everything and convert it into a linear layer, and then we combine the generator and the discriminator. There's a little bit of a noise dimension that they add at the start. And then for this one, they use binary cross entropy with logist loss for the discriminator, again, because it's binary classification. We're identifying which images are fake and which ones are real. Betas, you don't have to worry. You don't have to worry too much about the code, I'd say, honestly. A lot of this is overcomplicated for no reason. And then they use the same transformations that we applied, but they have a normalization which basically normalizes the data to a specific mean and standard deviation. Usually with image models, it's different values than 0.0.5. I don't know why they're doing this. This is very odd. Image normalization using, I don't remember those three numbers, but they're usually we use, it's like, yeah, we use these three, we use these 6 values as the mean and the standard deviation, not 0.5 and 0.5. But basically what's that doing is that we're basically standardizing each of the images to fall within a certain input distribution that our model can easily like do loss calculations on, right? Because if it's like, let's say all the pixel values are like at a certain end, it's going to be harder to update the loss. Essentially, we're able to reach the global extrema using the loss function. And then this is our training loop where we're implementing that informal training loop that we did here with the discriminator and the generator. Again, don't need to worry too much about the code. And the reason you don't have to worry too much about the code is because this also doesn't really seem to work. So this is some of the images generated by the generator part of the model, and it's not doing a fairly good job. And you can kind of notice this too with what they're using as their log with their logs, and you start to see that the discriminator goes from 1.34 loss to 0.81, but the generator goes up 10 times, right? So we kind of again we have that same issue where the generator's loss skyrockets, meaning that it's not able to produce images that are classified as fake or real. And then the discriminator is having a field day classifying those images, and the generator's output is basically not even close to the real images at all. There should be, before we wrap up, I know we have a little bit of time. There were a couple of cool ones that I wanted to show on GitHub. I don't know if I shoot. These are a couple of good ones. This is a better implementation of the network we just did, where I think, this one's generating those digits again, but does a good job. A lot of these are used for English. Yeah. So this one specifically, a lot of these these models can be used to kind of transform images into another type of images. So sometimes you may see like a night image and it turns into a day image, and that could be done using a generative adversarial network. So like for this specific example right here, you notice that these inputs are largely the same, but they're transformed a little bit. And what that would work is that you'd have this image and you had something like this in the training set, and then the generator would use this to produce something like this, right? And then compared to the actual version of this, and then the discriminator tries to identify the difference between this and the actual version of this, and then eventually the generator gets really, really good, and the discriminator also gets really, really good. And so kind of basically we want the discriminator to get really, really good so our generator can get also learn, right? We want our discriminator to give our generator a hard time so it can get better at generating. And sometimes, a lot of the times, that doesn't happen, and that's where our training process kind of fails with that. Okay. Anyone have any questions before we wrap up? Okay, so I think next time we're going to be doing transformers. Alvin's going to be taking care of that. Yeah, so that's going to be a fun one. I don't know. He said he might not do it. So.
Oh. Whoa, what is this pressure?
But
Doing great. I don't know if anybody's going to show up.
That should be that for today. Stop streaming.